Hi, in this video we will learn how to define a function out of an old function using a definite integral. Well, for that we assume that f is a continuous function on an interval AB. This can be actually any integrable function, but for us, continuous is enough. Then the definite integral of this function from A to B, we know is a number, yes? It's a constant. Well, for example, this constant for continuous and positive function is nothing but the area of the region under the graph of this function on the interval A to B. Yes, so it's a number. Well, it other than function f, it depends on A and B, which depends on values of A and B. Well, this dependence kind of introduces something that, well, we can maybe make one of these guys a variable. So instead of going from A to B, we can go only up to a variable, which is a number on the interval AB. In that case, so if that's positive function, so if you fix an x on that interval, it won't give you the area of the region under the graph of the function for the whole interval A to B. It will give you the area on up to x, yes? And while you can change that x, you can move it to left or right, and while you can get different values. For example, let me just do this. It can show a little bit, so I can do this a little bit and get the area of the region under the graph of that. So it will depend on x, and what will be a function of x actually is a function of x. Well, this function, you will see that is very important for us, especially in the fundamental theorem of calculus. In the next video, you will see how that plays an important role. And the rest of this video, I will try to do an example and find that function g for a given function f. So here the function g is this, defined as we had above. So from 0 to x, ft, and f is a function piecewise defined, and it is given by those formulas. So if you want to see the graph of that function, so that function will go before 0, it is just constant. Oh, let me do this for with other color. Then it will go up for 1 and then go down from there to -1. So this is 1, this is 2, this is 3. Then from 3 to 3, 4, 5, 6. See, between 3 and 6 it is another straight line, and then from there you have 0 function. Now, if you're looking for gx, you see that depending on x, we are going to deal with different things. For example, if x is less than 0, then gx is going to be integral of 0 to a negative number of ft dt. The integration is on negative interval, so we know that on negative integral, based on this part of the definition, the function is 0, and that will give you the formula for gx, which is 0. If x is bigger than 1, bigger than 0 and less than 1. In that case, well, a gx is going to be a area under the graph of a triangle. Like this is the first part, so let me just sketch that. But x is somewhere here, so we go x, this is 1, so we need to find the area of this one because it is integral of function t dt from 0 to x, and well, we know that this is equal to area of this triangle which has base x, a height x, and well, obviously it is half of x squared for that part. What will happen if x goes beyond 1? Well, up to 2, it is just straightforward again, because what we had above, now I can take it, copy. Oh, let me draw another one actually. So we have it goes up, then down here like that, and while it will have the whole triangle there, and before 2 it will generate this small right trapezoid, and the gx is going to be equal to area of this first triangle, which is now full. It goes from 1 up to 1, from 0 to 1, so it will have width, the base and height 1, plus the area of this trapezoid, right trapezoid. Well, you can find it by subtracting area of two triangles, but for me this is easier. Yes, so this is 1, and over there this is x up to 1, so this will be x minus 1, and the height of that, it is given by the function, which is 2 minus x. Okay, so the area of these two, you add these guys, you get half. Well, let me just write the final. You can do that one. Please try do it, complete it yourself. But the final result is going to be negative x squared plus 2 plus 2x plus 1. If x goes beyond 2 up to 3, then a gx in that case, well, if we sketch again the regions we are dealing with, we'll see that, well, there's a right triangle up there, then another triangle down up there again, then there will be a small triangle, so this one complete, this one complete, but then there will be another x, this is 2, this is 1, and this triangle here. What you have to know is that now we are dealing with 3 regions, so area of this complete right triangle, which is 1, 1, the width and height, plus area of another complete triangle, which is this piece. Again, this is 1, 1. But the last triangle there is in the below the x-axis, so we have to minus the area of that part. But what are the sides of this right triangle? Well, here you see from 2 to x, so we have x minus 2. And here, if you look the value of the function at x, if x is between 1, 2, and 3 is given by 2 minus x. But since this is a negative number, it will be x minus 2 again. And we have to apply those rules, and what you will see at the end, let me at least write. So you do some computations there, and what you will get is negative x squared over 2 plus 2x plus 1. And yes, you're right, these two are equal. so on the interval 1 to 3, the function is given by this formula. What happens if we go a little bit further? So if x is between 3 and 6, in that case we have this triangle, then we have this other triangle goes down, and then this goes like that. Yes, so we have one complete, another one, and then this piece also passed by, so this is 3, and now number is between 6 and 3, so x is somewhere here. And if you want to find the value of the integral, it is going to be area of, again, this right triangle 1 1 plus area of the second triangle, which is again a right triangle with 1 1 side and width, minus then the third triangle, which is below the x-axis, so it will be minus area of that piece there. But again, the signs, the values of the sides are 1 and 1. Then there is this trapezoid here, yes? So, and since it is below the x-axis, we have to do subtract the area. What are the values here? This is x minus 3 there. And well, if you use the value of the function, it will give you the negative of the length, which is 2 minus x over 3. This side is 1. So you do the work you need to do. The final number, final value for the function in this interval is going to be x squared over 6 minus 2x plus 5. And well, if x goes beyond this number 6, then gx is going to have 4 pieces again. Gx is given by area of the first piece, first triangle, then another triangle, which is, these are the triangles above x-axis, then minus area of the third right triangle, this is below x-axis, minus area of a fourth triangle, which is this triangle of this form, 1 1, and here will be 1 and 3. And you do work, all the work you need here. The number you get from this is actually -1. It will be a negative number. Now that I have all the values, I can write gx. Yes, gx is a function piecewise defined. If x is less than 0, it is going to be 0. If x is bigger than 0 and less than 1, it is going to be x squared over 2. I'm just writing the values we found above, and we saw that if x is between 1 and 3, it is going to be minus x squared over 2 plus 2x minus 1, and for x is between 3 and 6, this is x squared over 6 minus 2x plus 5, and if x is bigger than 6, then there is this negative. So you see that at least for simple function f, I can find the function g, which is defined from a to x for that given function f. Well, the example is done, but something interesting is that if you look carefully and you look at this function, you try to differentiate. This is a bad idea to have. Okay, red one. You can differentiate this function at least on the open interval. So if x is between 1 and 0, you differentiate, you get x. For x less than 0, you get 0. For x between 1 and 3, you get minus x plus 2. For x between 3 and 6, it is x over 3 minus 2, and for x bigger than 6 it is 0. Well, if you do a little bit more computation, good careful computation, you will see that exactly on the same points the derivatives are given by those formulas also. This function g prime, you will have seen this somewhere. If you look back to the original function that we started with, f, this is exactly the function f. And this is not coincidence. This we will study in the fundamental theorem of calculus part 1, and we will see that such a function has derivative, and the derivative is the function f we started